Okay, so this is our final coding workshop where we're going to use machine learning to diagnose COVID pneumonia from X-rays. We have one more workshop next week, which will be how to evaluate a machine learning paper or study. So first, since we're working with X-ray images, these are now image data files. In previous workshops, we used like a simple Excel list of data points. So those kinds of lists are really small and easy to work with. Images are quite large and you need lots of images to work with. So because the files are so large, you need more processing power. And what Google COLAB lets you use, if you go to runtime here, you can change your runtime type, and they have a GPU that you can use, a graphics processing unit that will make training on image data much faster. And they let you use it for free, although it will give you several annoying warnings that if you're not using the GPU, you should disconnect. But that's okay, we will be using the GPU. So I have uploaded a set of images onto Google Drive, and they are X-ray images. And the first thing we need to do is download them from the Google Drive. One option is to actually upload them here to the Google Colab files, but that will take hours to upload and nobody has that kind of time. So it'll take probably just as long to upload it to Google Drive as well, but to download it to Google Colab from Google Drive is fairly quick. And we'll use wget and all this complicated code, which I basically copied and pasted from another source. But what you do is when you go to your Google Drive, get the share link, it'll have this ID in it. So you need to replace the ID with the ID of your file. And that would be over here as well. So first thing, we download it. And it's in a zip file. All the images are zip file. We have normal chest X-rays, regular pneumonia X-rays, and COVID pneumonia X-rays. And I can show you a few of those. So these are some COVID pneumonia X-rays. Normal ones. And normal pneumonia. So this says our files have downloaded in the zip file, as you can see on the side here. Next, we need to unzip them, and we use the unzip command. -Q means quiet. That means it won't give you a whole list of things that it's doing. It will tell you all the files it's unzipping. And then you give it the name of the zip file. Then afterwards, we use rm for remove to remove the zip file once we've unzipped it. So that takes a minute or so. And we can refresh our files over here. There we go. Now we have our data. We have our test images and our train images. And then you can take a look at them there. So these are from a variety of ages. There's some children's X-rays, some adult. Okay, next, we need to import some libraries. We have OS, which is used for file management, sys for working with the system, date and time, random, which we use for generating random numbers, and TensorFlow, which is one of the main machine learning libraries, NumPy, very useful for working with numerical data, CV2, CV stands for computer vision. So this is a commonly used computer vision library, and since we're working with images, computer vision, we'll be needing that. And Matplotlib, which is useful for plotting things, making graphs. Pandas, which is used for manipulating data arrays. And then Keras, which is the very simple library for deep learning and neural nets, and several different things that we'll be using later on. There's a few extra ones there too. And then sklearn.metrics if we want to look at some more metrics. Okay, the first thing we need to do after importing is set a random seed. And what that means is we give TensorFlow a random, this gives a starting point for TensorFlow's random number generator. And if you want reproducibility of results, this is very important, because if you're going to, this will determine what the starting weights are. And if you're trying to reproduce your training exactly, or as closely as you can, you need to use the same initial weights. And this number can be anything you want. It can be 1, 2, 3, any number you want. Just if you want to repeat try and reproduce your results, you need to use whatever number you used the first time. Okay, now in our data, we have a test file and a train file, but we don't have a validation folder. So we need to make a validation folder. And this defines a function, and we can call it make val set. You can call it whatever you like. And we're going to give it two things. We're going to give it a path, which will be the file location, and a percentage. The percentage will be whatever proportion of images we want to take out of here to use for our validation. And I hope everyone remembers what the validation is used for. You use your training data to train the model, and then validation set will give you an epoch by epoch estimate of how well your model's doing. Okay, so we define this function, and we'll set our path equal to, so this line here, this is just an error. This helps to avoid human error. So what this does is it checks to see if the path -1. So this is the index, which means the way counting works in Python, you count with 0, 1, 2, 3, 4. But -1 kind of loops back around. So if you're at 0, -1 will be over here, -2, -3. So this is saying -1 of path, which will be the very last character in path. So for example, if I were to copy the path of this, that would be content slash data slash train. And the -1 would be the n here. So it's saying if that last character is a slash, then that's good. All's well and good. We can use the path as it is. If it's not a slash, in this case it's not, then it's saying add the slash. Okay. So since we've got a small group, is everyone familiar with coding, or is it fairly new to you? You can say in the chat, fairly new. Okay. A big part of coding is going through every little detail, bit by bit, make sure you understand it. I'm not going to spend too much time going through this, but I'll just go fairly quickly. So this is an error check. It adds a slash if there isn't one to the path. Then it makes this we've called images, which will be the source image directory. And this command lists all the files in a directory. And this will look in the train folder, the folder of path with train in it. Now for every image within that list of images, then we're going to ask it to make a directory, and it'll be a folder within that path called val. And then, see down here, we're not using the GPU. It's telling us to conserve energy, but we'll use it soon enough. This is saying to make a val subfolder, and it'll put an image in there. And if it already exists, then to ignore it. Next, we make a list of all the images in that our source folder or training folder. And then we randomly shuffle that list. Then we can count the number of files, total number of files. That's with the len command, len for length. So we feed file list into len. That'll give us the number of files in that list. And then we multiply it by our percentage to give us the number of files that we want. And last thing we do is we wrap it in this int, which turns it into an integer, because we can't transfer 4.5 files. It has to be 4 or 5. So int will turn it into an integer. And then we create a set of files, and we add the first n number of files up to the total number of files. So this is a for loop, which means for every n in our number of files, so let's say we have 200 files that we're going to transfer, it's going to take the first 200 files until it gets 200, then it'll stop adding to val set. And then for each one of those files in val set, then it's going to rename the path from the train folder to the val folder, which basically moves them all to our val folder. So I hope that kind of made sense. That's not the important part of this workshop, but data management is something that you'll spend a lot of time doing if you're working with machine learning. Okay, so this is just defining our function. Completely made sense. Good. Okay, so this defines our function. We run that, and now this is actually using the function. So make val set, make val set. Now we're giving it our path, and our path is this content slash data. If you're not sure what the path is, you can always copy path and paste it. And when you copy it, it doesn't include the slash, but that's okay. We have an error check. And then you can choose what percentage you want. We're going to take 20% of our training files and add them to our validation folder. Okay, now we'll refresh. There we go. Here's our validation folder. And we should now have about 20% of our original files. There's about, I think there's about 5,000 X-ray images in this data set. Okay. The next thing we're going to do is create a data generator. And what this is used for, previously in our other workshops, as I said, we used the simple Excel tables, CSV files, only a few 100 kilobytes of data. This time, because we're using 5,000 images, there's over a gigabyte of data. Usually when doing these things, you load all the data into memory at once. And with large data sets, that's not really possible. There's not enough memory. It'll just crash if you try to do that. Yes, it does remove them. So here in this last line, it renames the files. So the files are stored as, so our path that we inputted, in this case, it's content/data, and then it'll be the train subfolder, and then there'll be an image subfolder, which will be any one of these, and then the file within that folder. So this is the input file, and then we're renaming it to this. So we're changing train to val. So that'll basically move it to here because it's changing the path name. And often in your own computer, that's what's happening when you're moving files. You're not always actually physically moving the data from one part of your hard drive to another. It's just changing the reference to it. And then later, at some point when your computer's on and you're asleep, it's going to defragment the hard drive and move everything physically to speed things up, and so it doesn't get cluttered. But when you actually move something, it's basically doing this. Okay. So as I was saying, usual Excel, small data files can be loaded in memory, no problem. But with 5,000 images, there's not enough memory for that usually, unless you have massive computing power. So to get around that, we use, Keras has something called an image data generator. There's other kinds of data generators. But what this does, it will kind of take the images, like a couple at a time, and feed them into your machine learning model. And so there's only ever a few images in memory at a time. So first, what we're going to do, just to simplify things, we're going to assign train path to our training folder, make a val path for our validation folder, test path for our test folder. And as always, you can call these whatever makes sense to you. And then we're going to use an image size of 224 pixels by 224 pixels. This is a common input size used for certain convolutional neural networks, and we're going to be using a pre-made one, which takes this size input. Then we can set a batch size. We'll use 32 to start. And as always, there's never enough data. So we're going to use something called data augmentation, which means we're going to take our couple thousand images and make it to even more, tens of thousands of images. And we can do that by using different modifications to the images. So we're going to make a training data generator called a train data gen, and set that equal to image data generator. So this is the convenient data generator that Keras provides, and it has several different augmentation options that we can use. So what we're going to use is rotation range, which will rotate the image by a certain percentage, and we're going to say we'll allow it to rotate the image by 15 degrees either way, and it'll randomly choose to rotate an image anywhere within that range. And you want to choose a value that makes sense. For example, if you look at X-rays, like, people will shift around a little bit. They won't always be 100% lined up. But when are you going to see an upside down X-ray or a 90-degree X-ray? Like, that's pretty rare. That's not something you'll be seeing. So choose a range that makes sense. And then we're using a width shift, so that'll stretch the image by about, I put in 0.1, so that's 10% stretch. And then we have 10% height stretch as well. And then brightness range. This is the, so a value of 1 is the image as is, and 0.9 is 10% darker, and 1.1 is 10% brighter. So I've allowed it to adjust our images by 10% either direction. Then you can choose to zoom, and again 10% zoom in or out. And then I've added horizontal flip. Now, why would I choose horizontal flip? Do you ever see X-rays flipped around the wrong way? Probably don't see them flipped around vertically, and probably don't see them flipped horizontally either. But there is an interesting condition called situs inversus, where all the organs are flipped over. It does happen. And another advantage of doing the horizontal flip is that if your model is kind of focusing on something on a specific side rather than the actual appearance of a feature, then this could help to what do I want to say? It might help to reduce some overfitting problems with a horizontal flip. And then lastly, very important, is to scale the images. So this is usually most images, each pixel has a color range or an intensity range from 0 to 255, which would be a total of 256, which I think is 2 to the power of, is that 8? Someone can correct me. But that's like, if you ever go to the color picker on Paint, or anytime you're choosing custom color, you can input your color values, and usually you can put a number in from 0 to 255. So we want to convert that range to a range from 0 to 1. So we're going to divide every value by 255 in that image, and that'll rescale it from 0 to 1. So there are some other data augmentation options. You can shear the image, so that'll stretch it that way. This vertical flip. What else? There's a couple other things. Channel shift, I think that changes the color channel. You can rearrange the color channels. But we're going to use rotation, width stretch, height stretch, brightness, zoom, and horizontal flip for our data augmentation. And that's in our training data generator. Now we're going to make another data generator for our validation data. Because we're checking it against like real X-rays, we don't want to augment that. We just use the X-rays for the ones we're checking. It's just the training data that we want to augment. So the only thing we need to do is rescale it, and then we'll do the same with our test data, just to rescale it. And then, so we make a generator. Now we have to initialize it. So for that we use, you call it whatever you like again. This time we called it train generator. And you use the generator you already made and dot flow from directory. So this will allow you to flow the images from the directory into the machine learning model. And you give it the location of the directory, which we have here, and the size of the image that it's looking for. Actually, I just could have put image size here. And batch size would be the batch that we're going to use, and class mode. So in this case, in our previous ones, we've done binary classification, where it's either this or that. In this case, we're looking at three different things: a normal X-ray, a typical pneumonia, or a COVID-19 pneumonia. So this will be categorical. That lets you use multiple classes. And then just repeat the same thing for each generator. And I haven't changed these to image size, but it's basically the same thing. Okay, so now our data is set up and ready to go. We have a pipeline to pump it into our machine learning model. So now we're going to use something called transfer learning. Transfer learning lets you take a pre-trained model that's already out there and adjust it for your purposes. So I have previously downloaded the weights for something called ChecksNet, and I need to upload that now. Just drag and drop it into the side over here, ChecksNet weights. So while that's uploading, what ChecksNet is, it's a convolutional neural network. Keras has a ready-made convolutional neural network called DenseNet 121, and ChecksNet is DenseNet 121 that's trained on a very large chest X-ray data set, pre-trained, and it's been pre-trained to diagnose 14 different chest X-ray chest conditions. So we've already imported DenseNet 121 up here. That will let us use it freely. So first thing we need to do is define a function to load our pre-trained neural network. So we're calling it ChecksNet model. You can call it whatever you like, and it'll take a specific type of input shape. And down here we're using 224 pixels by 224 pixels by 3 color channels. So it's RGB. Okay. So first, we're going to create our checks net. We'll set that equal to a dense net, and include top means this is includes the very last layer of it. So this will be the classification layer, and we're going to remove that later. But for now, in order to apply the pre-trained weights, we need to include that. It'll make more sense in a second. And we're saying weights are none for the moment, and input shape will be whatever input shape we feed into it, which will be this down here when we do that. And number of classes are 14 because that's what ChecksNet uses. And we need to include top and have 14 classes in order to load the pre-trained weights. We won't be using 14 classes, and we won't be using the top, but we need to do that first so that it'll load it. Okay, next, we can create a new model, and that will be a model that takes inputs from here. So our inputs will be checksnet.input, and our outputs will be checksnet.layers-1.output. So this means the last layer, the output of the last layer, because -1 loops back around. And we'll name this checksnet base. So that'll be our base that we're using. So this line will load the dense net, and then this creates a model out of it. Now we need to load the weights, and it's simple as checks model.load weights, and I've already uploaded these over here and just put in the path to those. And then we're going to say that this model is not trainable. So checks model.trainable equals false, because we want to use these pre-trained weights because they're already effective. So we can choose to make them not trainable. Okay, so these lines basically loads checksnet as is. Now we need to modify it for our purposes. So we're going to say, so checksnet was trained to identify 14 different chest X-ray conditions, or 14 different classes. And this set of weights was pre-trained to looking at those 14 classes. And I'll provide links in the notebook afterwards for more information. Okay, so this is checksnet as is. Now, to modify it for our purposes, we need to we'll just make something called X. You can call it whatever you like. And we're going to say X is equal to the second last layer, the output of the second last layer. So that'll be the output of checksnet without the final classification layer. And then we're going to say, so we have X. Now we're going to redefine X as create a new dense layer. We're going to add a layer of neural network on top of the checksnet, top of the convolutional neural network. And ReLU activation, you can name it whatever you like. This is fully connected layer 1. And at the end of that layer, we put our previous X. So whatever's in brackets here will be the inputs of this layer. So this is the output of our checksnet. And then we create a new layer that takes that output as its input. And I've chosen 1024 neurons for this, or nodes for this layer. You can try different numbers, see what works. And I've added 3 of those layers. So here's another one. This one takes the previous X as its input. Each one takes X as its input, but since we keep redefining it, it's taking the output of each layer as the new input. And then just before our final classification layer, we're putting in some dropout. And hopefully you remember dropout. That will randomly inactivate, in this case, 0.4 or 40% of the nodes or neurons in the previous layer. And that's a safeguard against overfitting. And then our last classification layer will have 3 outputs because we're looking at 3 different classifications: normal, typical pneumonia, and COVID pneumonia. Activation function this time is softmax, which lets you use different categories. This gives a value anywhere between 0 and 1. And yeah, that'll be our last layer. So now we take, now that we've defined our new layers, we make a new model, call it model. And this model takes the inputs from our ChexNet inputs, so the very first inputs. And then the outputs this time will be X. And you can call it whatever you like. Call it ChexNet. How about actually ChexNet modified? And then return model. This will be important because if you don't return it, then the function really won't do much. Now we'll say model equals our function ChexNet model. Give it the input shape 224 pixels by 224 pixels by 3 color channels. And then we're going to do model.summary, which will give us a look at what the model actually looks like. And once I do that, hopefully all of this will make a whole lot more sense. Okay, we'll run that. Okay, now this will show you all of the layers within the neural network. And it's DenseNet 121, so it might have 121 layers maybe. So there's input layers, convolutional layers, normalization, max pooling, whole lot of layers, and it'll starts with 224 pixels, shrinks it down each time to try and find just the features, going down to 28 pixels, 14, those are the convolutions, 7, and now, so here is where, this is where the ChexNet ends, and this is where our new layers start. So we've stripped off the final classification layer, and we've added our fully connected dense layer, 1024 neurons, and then a smaller one, 512, and another 256, our dropout layer, and our final classification layer. Okay, so now we have our model. It's pre-trained on the ChexNet XRAY database, and we've added a few new layers to help it figure out our our own data. Next, we can choose a learning rate, and this is a typical one. Use a number of epochs. So I've already pre-trained this on 40 epochs. I'm not going to do that now, because that takes about an hour to train. So we'll just do 3 epochs for demonstration purposes. And then optimizer using its Atom, fairly common one, and set learning rate equal to learning rate. And then we compile the model.compile. We give it a loss function. And this time we're using categorical cross entropy, which allows you to output multiple categories. We're going to take a look at the accuracy metric and give it the Atom optimizer. Okay, and we'll compile that. Next, we need to fit our model to our data. So we can call the results of that history, because it'll help us look back at it later. And we model.fit. So when you're fitting the model, you use .fit. And we're going to feed it our train generator. That was the data generator we made way up here. So we give it our training data generator, tell it how many epochs, which would be 3. Verbose equals 1. Verbose means basically how much of if you set verbose to 0, it won't give you any progress updates or it won't tell you what it's doing. So verbose equals 1, it'll tell you what it's doing. If you put verbose equal 2, it'll tell you a whole lot about what it's doing. We're going to use verbose equals 1. And then our validation data is going to be our val generator. And that's all we need to train the model. And we'll hit run. Why is it not? Did I not run this? No, I didn't run it. Okay. Oh yeah, when you run it, it tells you how many images are in each generator. So in our training set, we have 4,116 images, 1,028 in our validation set, which is about 20% of what it was. It was 5,000 before. And then 1,288 in our test data set. Okay, and now this should work since I actually ran that cell before. And this will take a little bit of time. And while that's doing that, I'm going to upload my pre-trained file. And as you can see, this takes a whole lot longer than previous workshops. When you're working with image data, you might want to set this up to run overnight and then go to sleep and then see how it looks in the morning. Or if you have access to. So where to find pre-trained models such as ChecksNet. For example, looking for pre-trained model for echo images. Well, if you can find a paper that is describing a model that's already worked for echo images. Sometimes they'll provide links to their data, links to their model. Usually they're posted on GitHub. Sometimes you need to contact the authors. Basically, there's no real easy way to find it, but got to do some Google searching. You can look on Kaggle, for example. Usually there's a lot of data and weights posted on Kaggle. Okay, so as you can see, our first epoch took about 2 minutes. So any published code can work here as a pre-trained model. Yeah, pretty much. Yeah, if like you can save, train, and load pre-trained models, and we're going to run through that in a bit. But yeah, you can copy and paste code. You can if the pre-trained weights are available, you can download those and apply them to the model. Keras has already some uh, neural networks already made, such as the DenseNet 121, where we just have to call it by name. Some you need to list like layer by layer in code. But anything will work. Okay, so let's take a look. We've got one epoch done, 2 more to go. And what do we have here? Okay, we've got our loss is pretty high, accuracy is high. Same with validation loss. That's typical on the first run. Second one, loss is going down, accuracy is going up. Validation loss also going down, validation accuracy also going up, which is always a nice thing to see. And if you remember, when the training loss is going down, but the validation loss is going up, that means you're overfitting. It's learning the training data way too well, to the point where it's picking up on unimportant data that's very specific to the unimportant signs that's very specific to the training set. Okay, so we've got another 10 seconds before our 3 epochs are done. Okay, and there it is again. Loss is going down again, accuracy is going up again. Loss went up this time, accuracy went down, but that's common in the first couple of epochs. You'll find that with about 40 or so, it'll decrease quite nicely. And then this is some code just to graph it. I'm not going to go through that in detail, especially since we're a little low on time. But that'll graph training accuracy, validation accuracy. Not very pretty with only 3. But the next thing we can do is evaluate the model. So once we've trained the model, we can evaluate it on our test set. So this uses model.evaluate. And then we give it our test generator. So we've used our train generator, and we've used our train generator, our validation generator. Now we're using our test generator to evaluate it. Won't look great at the moment because it's only trained 3 epochs. But it won't be too bad. And there we go. On our test data, this test data is data it's never seen before. Accuracy is 84%, almost 85%. That's pretty good. That's because it's been pre-trained already. Okay. So and then you can save. Once you've trained the model, you can save it. You can tell it where to save it. So in this case, it'd be here as saved model, and you can so you save model and you give it the model, which we've called model, and give it the save path, which is here. And if you hit that, it'll save it. I've already, well, after you save it, you put it in a zip file for easy download. I've already done that on the previously trained one on 40 epochs. On that one, I got 90% accuracy on the test set. So now that we've trained it, well, only 3, but now that we've given our data to our model, our transfer learning model with the ChexNet as the base, We've tested it, it works pretty good, we've saved it. Now let's say we actually want to use it to predict things. How do we do that? Well, first I'm going to load this previously saved model. So first I'm going to unzip saved model, and our model is here. I did it in another content folder, but that's okay. Okay, now we'll load the model. And pre-compile it. And that takes a minute. While that's loading, next we need to give it some files that we're going to predict. So I'm going to make a folder, call it predict. And I'm going to upload some test images that we're going to predict. Again, we'll redefine our image size. And we're going to tell it where these images are. So our X-ray images are in, we're going to make a list of those images, and they're in predict path, which is here in content slash predict. Oh no, wait a minute, here we go. It's in content predict, so that's here. And now this saves it as a list. And we can print out that list. Actually, let's do it this way. And now it's all stored as a list of file names. Now we'll make an empty list called data predict and say for every X-ray in this list of X-ray images, then add the name X-ray, the name of the file, to the predict path, and that basically creates the full path of the image. So the X-ray path, and then X-ray image we're going to set to, this time we're using that computer vision library with its image read function, and it's going to image read X-ray path. Basically, it's going to convert it into an array that the model can use. Okay, we've done that, and then we're going to normalize it. Again, we're dividing by 255, and we're telling it it's a float, which is a decimal point image, a decimal point number instead of an integer. And then we'll resize it to our image size. It takes this input itself, or this previous version of itself, X-ray image, and our image size, which we have here, 224 by 224. And then we append to our list the image. So basically adding the image to our data predict list. And then we convert that into a NumPy array, which is something that's readable by the neural network. Okay, that will load the data. Now we can tell it to do our predictions. So let's put this in a new cell here. So then we can say predictions equal to model.predict. Fairly straightforward. Again, this is our model that we've loaded, and it's going to predict from our list of these images. And we're going to print the predictions. There we go. Perfect sense. Now you know what's COVID, what's not. Not really. Okay, so what does all this mean? So each of these numbers are basically the probability. This will be like image 1, and this is the probability that it's normal or COVID or pneumonia or whatever. So in order to figure out which one is the one we want, we're going to say for each image in this list of predictions, in our predictions list, we're going to say that X-ray prediction, which is the array, is equal to classes. So we've made a list with our classes, and we use this function called argmax, which means it'll take whichever number in that set is the biggest, the maximum. It's going to set it to 1. And so if this one is 1, if this one is, or it's not going to set, it's going to return the index of whichever one is biggest. So if this is biggest, it's going to return 0. If this is the biggest, it's going to return 1. If this is the biggest, it's going to return 2. And then it'll print out those predictions. So if we run it and compare it to our list up here, thinks the first one is pneumonia. It's pneumonia. Second one is COVID. It's COVID. Third one is normal. 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 Pneumonia, COVID, normal, pneumonia. Pneumonia, COVID, normal, pneumonia. 100% accuracy on these few images. And it won't always be 100% accuracy. I got lucky with these few that I selected. And you might wonder, we never really said which class is which. But one thing you can do is set it to 0, 1, 2, run it, and these will give you the predictions. And so if all the 2s are pneumonia, as they are, then you know that 2 is pneumonia. If most of them are one class, you know that it's going to be that one. And again, the 0s COVID, and the 1s are normal. And of course, if you want to do some more coding, you can figure out how to make a graphical user interface with buttons that you can click on, and like a file system that you can load files and make it like a nice, easy to use interface instead of all this code. All right, that is it for how to detect COVID pneumonia with machine learning. I hope it makes sense. I tried to keep it kind of simple. Any questions? Hope it all made sense. There's a lot of code in here, and even if I did a good job making it sound simple, when you actually sit down and go through it, you'll find that every line has some nuances to it that you can spend a lot of time learning about. Okay, so if there are no questions, that concludes our workshop, our coding workshop series. And I'd like to take this time to ask for some feedback. Let me just stop recording.